Hello everyone, welcome back. Today we're going to talk about Chapter 3, Part 1, which is radiation. Radiation is very important because it gives us information about the universe, about everything we see. In this opening picture right here, we're seeing a stellar nursery, which is a young nebula that comprises about 2,200 stars. Now our sun, our own star, emerged from a stellar nursery similar to the one shown here about 5 billion years ago. Now in this chapter we're going to cover electromagnetic radiation, waves, thermal radiation, and the Doppler effect. So let's start with light. Starlight is going to waste. Every night it falls on trees, oceans, parking lots, cars, and it is all wasted. To an astronomer, nothing is so precious as starlight. It is the only strong link to the universe. So the astronomer's quest is to gather as much of it as possible and extract from it the secrets of the heavens. The telescope is a symbol of the astronomer because it gathers and concentrates light for analysis. Most of the interesting objects in the sky are faint, so astronomers are driven to build huge telescopes to gather the maximum amount of light. Some telescopes collect radio waves or X-rays, and some go into space, but they all gather information about our universe. Now, this picture right here is a picture of the Andromeda galaxy. It kind of looks like a pancake. It's a spiral galaxy, and it is about 2.5 million light years away from us. Now remember, a light year is a measure of distance. That means it takes light from the Andromeda galaxy 2.5 million years to get to us. Now, what is light? Well, light is peculiar because it is both wave and a particle. And how it behaves depends on how we observe it. So light is a form of electromagnetic radiation and has the ability to carry energy through space as electric and magnetic waves. We use the word light to refer to electromagnetic or EM radiation that we can see. But visible light is only a small part of a larger range that includes X-rays and radio waves. Now, electromagnetic radiation travels through space at what we call the speed of light, which is 300,000 kilometers per second, or 186,000 miles per second. Now, some people flinch at the word radiation, but that reflects a common misconception. Radiation refers to anything that radiates from a source. High-energy particles emitted from radioactive atoms are called radiation, and you have learned to be a little bit concerned when you see this word. But light, like all EM radiation, spreads outward from a source, so you can correctly refer to light as a form of radiation. Now, electromagnetic radiation can act as a wave phenomenon, so it can be associated with a periodically repeating disturbance, which is what we call a wave. Now, you're all familiar with waves in water. If you disturb a pool of water, waves spread across the surface, just like shown in the picture there. Now, imagine that you use a meter stick to measure the distance between the successive peaks of a wave. This distance is called the wavelength. Now, notice that once you do that, the water moves up and down, but the wave travels across, and it is what transmits the energy. So if you look at the little inset in the picture, the top one shows the undisturbed pond surface, so nothing is happening to those 5 particles pointed right there. Once we disturb the pond, we see this wave pattern, this going up and down. And notice how particle 1 moves up, then goes back down, and then goes down lower. And the same thing happens with particle 2, 3, 4, etc. Now the particles themselves are oscillating or vibrating up and down, but the wave, it's moving outsourced from the source. So that's why you see that little arrow pointing towards the right. That's the direction of wave motion. So wave motion, I want you to think about it this way. It's the transmission of energy without the actual transportation of physical matter. So the particles in the water are not going anywhere. They're vibrating up and down, but the energy is moving outwards. Now, we talked about the successive peaks of a wave as the distance called wavelength. And in that picture right there, you can see wavelength going from peak to peak. Amplitude of a wave, meaning how high it goes, is the distance indicated by the arrow there. Now troughs are the minimum points of the wave and crests are the maximum points. In an undisturbed state, we don't have this oscillating up and down motion, we just have the flat line that is shown as a dashed line over there. Now, wavelength is given the Greek symbol letter lambda, and is the distance between the successive crests. Now, a frequency is the number of wave crests that pass a given point per second, and it's given the symbol little f. Now, period, we've seen this word before. So, period in terms of waves is the time between passage of successive crests. So how long does it take to do a whole wavelength is the period. In terms of circular motion, which we talked about before, is how long does it take to go around in a full circle once. Now we have a relationship for finding the velocity of a wave based on its wavelength and its period. So if you look at the bottom right there, we have a formula. Remember, V stands for velocity, and that's equal to the wavelength. And wavelength is going to be measured in meters because it's a type of distance, divided by the period, which should be measured in seconds. The visible spectrum. Now, what is the visible spectrum? It's basically part of the electromagnetic radiation that is visible to human beings. Human eyes are sensitive to radiation of wavelength between 400 and 700 nanometers. Nano is a prefix that stands for 10 to the minus 9. So what we can see with our human eyes falls in the wavelength of 400 and 700 times 10 to the minus 9 meters. Now, if you picture a prism and a flashlight, and you put light through the prism, then the white light splits into its component colors, spanning red to violet in the visible part of the spectrum. What the slit does right there, it narrows the beam of electromagnetic radiation or light. This familiar rainbow of colors can be projected on a screen, and you end up seeing the rainbow between red and violet. Now, of course, there's radiation outside the visible range. It goes all the way from radio waves to gamma rays that we cannot directly see with our human eyes, but we use different instruments to analyze that part of the light for us. Now, why is light so important? because the only things we can learn about objects and phenomena outside our solar system are learned by analyzing the light they send to us. So in a sense, astronomy is all about how to collect, analyze, and interpret the light that's coming out from the cosmos. Now remember, I want you to consider light as both waves and particles, and that's going to depend on the circumstance. And what do I mean by that? Well, that's actually one of the big mysteries in quantum physics, is how it can behave in both ways. Now, either way, it's common practice to call the particle nature of light photons and the wave nature of light electromagnetic radiation. So when we're referring to light as particles, so that's our circumstance, then call it photons, and we're referring to light as waves, we call it electromagnetic radiation. Now I'll put a link right here on YouTube to the Science Theater, and this is about 7 or 8 minutes long, and it talks about waves, the nature of waves, and how they oscillate up and down, but the motion and the energy is sideways. So please take a few minutes and look at that. This is a very good representation of what's taking place. All right, so we're interested in waves and in light. Now the question is, waves in what? There's several types of waves. There's the water waves. We talked about when you throw something in a pond and it ripples out. There's also the sound waves, and so on and so forth. Earthquake waves. There's lots of types of waves, but they all travel in a medium, so they need something to go through. For example, sound waves, they need air to travel through. So for example, if you're on the surface of the moon and you talk, nobody's going to hear you because there's no atmosphere to carry the sound wave. Now, electromagnetic waves, light, needs no medium, which is a good thing, which means that we're able to receive light from things out there in space. Now, what creates electromagnetic waves is what we call accelerating charged particles. Now, what is a charged particle? A charged particle is a subatomic particle that has what we call a charge associated with it. You must have heard of pluses and minuses and things like that. Opposites attract, similars repel. Well, if you look at frame A, you have two pluses, so you have two particles that have a plus charge associated with them. Because they have a similar charge, meaning they're both pluses, they're going to repel. As they get closer, they're going to have to move away. They're going to be repelled. And the same thing happens with the minus situation right below it. Because it's similar charges, they're both minuses, they're going to want to repel. However, on the bottom right, you see a plus and a minus. They're opposite charges, and opposite charges attract. Now, frame B is showing the electric field lines. Electric field lines are associated with any kind of charged particle. So if a particle is positively charged, it's going to be emitting electric field lines outwards in all directions. If you have a negatively charged particle instead, it's going to have electric field lines pointing towards it from all directions. So if you have a plus and a minus, you can envision an electric field line leaving the plus, which is indicated with an arrow pointing towards the right, and entering a negative charge going into that charge. So remember, electric field lines leave positive charges and enter negative charges. And that's how we have attraction. Now in frame C shows a situation where you have a charge, but it's not just sitting still, it's vibrating up and down. It's vibrating up and down, it's creating a kind of a wave. So its electric field lines still leave that charge and they enter the distant charge in an oscillating manner. So electromagnetic waves are basically oscillating electric and magnetic fields. So just like you can have electric field lines leaving a charge, you also have magnetic field lines. Now, a changing electric field creates a magnetic field, and a changing magnetic field creates an electric field, and it is that combination that we call light. Now, notice how the blue line in this picture is a magnetic field vibration, the oscillation we talked about, and the red wave is the electric field vibration. Notice how they're at 90 degrees to each other. When we have this kind of situation, then we have the wave motion, and notice how the direction of the wave motion is at 90 degrees to both the electric and the magnetic field. So electric and magnetic fields vibrate perpendicularly to each other. Together they form the electromagnetic wave that moves through space at the speed of light in the direction perpendicular to both the electric and the magnetic fields that make up the wave. So what is the wave speed of electromagnetic waves? Well, since electromagnetic waves are light, their speed must be the speed of light. And even though it's a speed, instead of giving it the symbol v for speed or velocity, we give it the special symbol lowercase c. Whenever you see c, then you know we're talking about the speed of light, which is 3 times 10 to the 8 meters per second. This is a very good number to remember. This is one of the very few numbers that I would like you to learn. Now, this speed is very large, and we mentioned this before. It is the speed limit of the universe. It's very large, but it's still finite. So it takes light millions or even billions of years to traverse the astronomical distances that make up our universe. So this means that we see distant objects as they were in the past, not now. And this is a key point. This is very important. So let's take a look at example, the Andromeda galaxy, which we already said is 2.5 million light years away. So when we pull out our telescope and we observe the Andromeda galaxy, we see it as it was how long ago? As it was 2.5 million years ago, because this is how long it took light to travel to Earth. So that's pretty amazing. So it is literally like seeing back in time. Now, if anything has happened to the Andromeda galaxy, some super high-power, technologically advanced aliens that somehow can wipe away a galaxy, we're not going to know that for 2.5 million years. Now, there's energy associated with the photon, the energy that is associated with the wave. So that energy can be found using this little neat formula right here. Capital E stands for energy, little f, remember, is frequency, and c is the speed of light. So the energy of a photon, or electromagnetic radiation, can be found by using Planck's formula, which is E equals F times C. So that is a very useful formula. Which brings me to the whole range of the electromagnetic spectrum. So what is a spectrum? First of all, a spectrum is an array of electromagnetic radiation displayed in the order of wavelength or frequency. Now, note that as wavelength increases, so take a look at the third line there that says wavelength in meters. So as wavelength gets bigger and bigger and bigger, we're moving on from gamma rays all the way to radio waves. And if you look at the line above that shows frequency, frequency is decreasing as wavelength is increasing. Now the units for frequency are hertz, which is 1/2. So as frequency decreases, okay, wavelength increases. And as frequency increases, so if we head towards the right, towards gamma rays, at a frequency of 10 to the 23rd, notice how the wavelength has decreased. It looks like it's squished in, smaller and smaller. Now, in terms of the scale, just to give you an idea, the whole EM spectrum ranges from radio waves, microwaves, infrared, visible, ultraviolet, X-rays, all the way to gamma rays. Just to give you an idea of the sizes of this, a radio wave can be as big as Mount Everest, and it gets smaller and smaller. So think of the skyscraper size, then think of the human size. When we get to microwave range, it's towards a fingernail or a pinhead size. Infrared is down to the dust size. Visible and ultraviolet, we're talking about the sizes of bacteria and viruses. X-rays, we're talking about the sizes of atoms. And down to gamma rays, we're talking about things that are very, very small at the atomic nucleus size. So different ranges of the electromagnetic spectrum have different names. They have different names because they have different wavelengths or frequency associated with them. And just like we said before in Planck's formula, if we have a different frequency, then we have a different energy. Now, gamma rays are harmful to us because, as you notice, the frequency is 10 to the 23rd. Because the frequency is very high, the energy is very high, which is why gamma rays are harmful. Now, I want to point out the bottom of this picture right here that talks about opacity in Earth's atmosphere. Now, Earth is transparent to only two windows, what we call the radio window and the optical window. Everything else gets absorbed by the atmosphere. It either gets absorbed or reflected back. What goes through from the top of our atmosphere all the way down to the ground is the radio part of the spectrum and the optical part of the spectrum, which is why astronomers build radio telescopes and visible light telescopes and leave those on the ground. Anything else we want to look at, we have to build a telescope, an X-ray telescope, for example, would have to be launched above the atmosphere to be able to observe in the X-ray spectrum. So that's very important to remember, the two windows of transparency on our planet. Here's another picture of the electromagnetic spectrum. Again, on the very top, we're seeing that gamma rays have very, very small wavelengths. You see how the wavelength is getting closer and closer. And then we go all the way to radio waves, and the wavelength is stretched out. The visible part of the spectrum, which remember is what human eyes can interpret, is a very, very, very small part of the electromagnetic radiation spectrum. Now, put this picture right here, and it's not in your book, because down on the very bottom, it shows the cosmic sources of different types of radiation. For example, if we want to see the gamma ray burst, and we're going to talk about which celestial objects create that, then we need to look into the gamma ray of the spectrum in order to actually see them. If we want to observe black holes, then we need to be looking at the X-ray part of the spectrum. Now, if we want to look at the sun directly, then that's in the visible. Remember, never look at the sun directly without a filter, though. Now, planets or star-forming clouds, then we shift to the infrared. When we want to look at the cosmic microwave background radiation, then we need to be looking at the microwave part of the spectrum. And when we start talking about radio galaxies, then we need to shift to the radio part of the spectrum. So astronomers use the whole range of the electromagnetic spectrum because it all gives us information about what's taking place. your book has a little part on discovery, the wave nature of radiation. Remember how we talked about radiation or light being both a wave and a particle? So I put a nice link on YouTube. It's about a 12-minute video on Dr. Quantum. And Dr. Quantum goes through and explains the double slit experiment, which is what got physicists to understand that light can behave in both ways, as a wave and a particle. So he goes through that and explains that, and I think it's worth your time to look at that. Now, here's a representation of one slit. Diffraction, which is the spreading out, is purely a wave phenomenon. So it's a spreading out of a wave as it goes through a small slit. Now, if light were made of particles, we would not see it spreading out, but we would just see a spot on the screen the size of the hole. But what happens with light is that we end up seeing both things. So this video explains that step by step, so I would recommend that. Now, I also want to talk about the different temperature scales because it's going to come in handy on the second part of chapter 3. Now, you're all familiar with the Fahrenheit scale. In Europe and some other countries, the Celsius scale is used instead. And in science, in physics or astronomy, we use the Kelvin scale. Now, notice how water freezes at 32 degrees Fahrenheit, which is equivalent to 0 degrees Celsius, which is equivalent to 273 degrees Kelvin. Now, all thermal motion, subatomic or otherwise, stops at what we call the absolute zero temperature, which is 0 degrees Kelvin. Now, nothing is that cold. Even the space between galaxies in the universe is not that cold. Even that space is a few degrees Kelvin, anywhere between 4 and 10 degrees Kelvin. So nothing is as cold as 0 Kelvin. That is the absolute zero temperature where any kind of motion or vibration on the subatomic level ceases to take place, what we call the cold death. So I want you to keep in mind of these three scales, especially the Kelvin temperature scale. So we covered chapter 3.1 through 3.3. Light and its properties are possibly the most important concept to understand in this course. Remember, spectrum, electromagnetic spectrum, or radiation or light, they all mean the same thing, is a mixture of light of different wavelengths from a given source. And this is going to come in very handy on the next part.